usually I talk about computer security, and we go down the far end of the rabbit hole, so to speak. This time, it's more of an intro talk on how to build a supercomputer-like facility using very cheap hardware. And the idea is that we want to go on every single detail and make it very easy to do this, and to do this relatively quickly. So let's get going. So my former head of product marketing had always this rule that you had to introduce yourself, and so here's me. Like they were saying, I'm a product management director at Red Hat. If you go back, the decade, I've worked on pretty much every Linux distribution you can think of. A few systems management products associated with that. SUSE Studio for those who remember it, Landscape for those who use Ubuntu. Ximian Red Carpet if you go back 15 years. And for about 10 years, I was the maintainer of the Man Pager. And the reason for the funny picture from my publicist is that I wrote a book about Amazon AWS systems management. So that's enough about me. The usual obligatory disclaimer about hardware is that we'll break some, and it will be out of your pocket. So there are no warranties if you bring out the end of the world or stub your toe doing any of the following. I think it's not very likely in this talk, frankly, but there is always some smart aleck that manages to destroy some hardware, myself included. So it's just so. Let's look at how this came to be. So if you look at the table, there are two Pi clusters here. One is a Pi 3 cluster, and the other one is a Pi 4 cluster. So I need to change the screen to do this. And I'm going to use pictures because your eyes may be better than mine, but they are not good enough to see these. So this is a Pi 4 cluster. This is the Pi 3 cluster. You can kind of see that the Pi 4, because of USB-C and not much else, is twice as big. Obviously, it's more powerful, but not because of what you would expect. Really, what we want out of the Pi 4 is the switch, as it will be obvious towards the end of the talk. Pi 4s have actual gigabit Ethernet as opposed to the 4 gigabit Ethernet of the older Raspberry Pi. So this is pretty much a combination of existing hardware and self-built. This is the part that's self-built. Cases from Monoprice fit very well to carry this around, and both clusters made it across the US without breaking, so that works. The Pi stack pretty much looks the same for both clusters. It's a stack of boards held together by standard brass or, in this case, nickel standoffs. Nothing too strange. The kit with the pre-cut plexiglass was made by a company called Pico Cluster out of Utah. I think they are in Orem, but they're somewhere in Utah. These kits come with power distribution units that are already pre-built, so I didn't need to design any of this. The one for the Pi 3 is simpler. It's a simple USB, standard USB switch, and it can also carry data. The other one is a more complicated custom board to distribute USB-C power. And since there are higher voltages there, you can actually get blue smoke out of the big cluster if you don't pay attention. Here you can see pretty much how the build progresses. This is the complete stack for the Pi 3 cluster. And then you have the wiring, which in this case is pretty simple. It's all USB and an extension to bring out the HDMI. I think what's most likable about the Pi 3 cluster is how compact it is. And now it's also even cheaper, which helps. But the compactness is the nicest part. You can see there on the left the single power entry point and the HDMI for node 0. only the head node has video access. This is the standard way the cluster is built. Those of you that can see this far will see that my version is slightly different. I found a switch that fits on the side and incorporated that. And I had to do a few things to make that work. Software checkout, we'll go into it in a second. So that's what I was just describing. So we have 5-port switch, and we just bring out the physical Ethernet. Nothing too strange here. We extended the cluster a little bit with Pi Moroni blinked LED arrays. So obviously, it's a supercomputer. It has to have blink and light, and it does. And we'll get to that in a second. I don't have a picture of it, but the only problem that's left in this design is that there is no clearance for the power supply of the switch. So I had to go on eBay and find an elbow connector to turn the power 90 degrees so that it wouldn't hit the table. The rest is all pretty straightforward. The Netgear switch fits the size of this perfectly. So that's about the assembly and the hardware. We're not going to discuss what's in a Raspberry Pi 3 and a Raspberry Pi 4. We have better things to do. You already know all of that. Let's look at the software. This is the part that's interesting. So how do you make a bunch of different computers into a cluster? So first of all, this is a simpler kind of cluster. It's a numerical computing cluster. So we're not building a cloud, and that makes things a little bit easier. We just need to have users to distribute the workload across the nodes. We simply set up root, just because it has no password by default. Using the Pico cluster stock images, they come with a user called Pico cluster. You want to rename it to yourself or whatever you want it's called, because once you start, it gets very hard to do. You want to do this right at the beginning, and you want to nuke the X-authority file so that it doesn't block you because it's locked to the old user. So that's how you rename the user to whatever you want. And we're not going to see that live because it's not worth our time. But in the end, we have a cluster with your personal user and root, just in case you need a second user to be able to do operations. Maybe you lock yourself out of your account, or who knows what else happens. Root does not have SSH access, so if you're going to really lock yourself out, you maybe want a third account. Because of this flat structure where all users are the same in name, in UID, even in password, but we're not relying on that, across all nodes, this is relatively simple in terms of NFS. There is no NIS, there is no authentication. This is probably the only case where NFS is actually easy. And right, you could have a second unprivileged user Pi just in case. In this, I guess I got comfortable enough that I don't have that. Pi or ops are the usual choices. Let me see. If everything is working correctly, now we are connected to node 0. And we can see that I was logging in earlier today, trying to make sure that everything worked. No surprises there. So let's get to something slightly more meaty. What is the network laid out like? So we have 2 networks because we're using Raspberry Pis 3s and 4s, and this is actually pretty cool. We could do it with 1 network, but it would be slightly more complicated. Because we have 2 networks, we use the wired network for the compute purpose. So we hard code IP addresses to each board. They are fixed. It's always 10, 1, 10, 240 for the head node, and on from there. In this case, I have 3 nodes. You could have 10 or 20, it doesn't matter. These are always at this IP address, which makes coding your computing application, your numerical application, very easy. There, you can rely on the board name. You can rely on the IP address. It doesn't matter what happens. These are going to be fixed, which is typically not the case when you move a cluster. So usually clusters are unmovable because if your application is in any way depending on what you have in terms of IP addresses, it's going to have to be rebuilt. You could use DNS, but most of the time there is something getting stuck somewhere, even in enterprise class products. I know firsthand. But certainly in scientific code, where everybody gets pretty sloppy pretty quickly, you will never be able to move the hardware unless you do this kind of thing. So separating the network works really nicely. I have the physical network dedicated to the application. The cluster can be taken around to conferences, and it will just continue to work. The part that gets adjusted is the Wi-Fi network. The Pico cluster, by default, turns off the HCP so that it doesn't interfere and it doesn't change any IP addresses anywhere. So they ship with Wi-Fi off. We did one better, and we turned Wi-Fi back on, and we set it up correctly so that it is secondary to the physical network. So if you have Wi-Fi, it is primary for world routing. So if you try to install a package or update a package, it will go out through the Wi-Fi. But if the Wi-Fi is not connected or doesn't exist, it doesn't affect the operation of the wired network. So how did we do this? We did two things. One is we introduced the WLAN configuration of the interface in ETC network interfaces. And the thing here that is worth calling out is that we set up WLAN 0 before we set up ETH 0 on each node. And by doing this, if WLAN 0 gets configured and gets connected to a Wi-Fi access point, then the default route will go through there. So we don't need to muck with the routing. The default routing goes automatically in the right place. If WLAN 0 does not connect, then the default routing goes to ETH 0, and there is no interference with your code. And the way this plays out in practice is, well, we'll see if it plays out correctly. Yeah, it looks like it did. It's default routing to the scale network, and it has a local route just for our compute nodes. And we have WLAN configured and ETH0 configured. Now, this, if you're a virtuoso of Linux network configuration, you can do this just with one network. But it's not this simple. And since this is either something that you could use like I do to define processes and how you manage clusters, and just having a small cluster is good enough for me, or the other application that you can have is teaching. The fact that this is way simpler than advanced Linux network configuration makes it ideal. So the other side of the configuration is that you have to configure the WPA supplicant to get you on the Wi-Fi network. And once you've done this, now you can install new software as needed through apt, usual thing, and you are even ready to visit Red Hat because you have our guest network password right there. Actually, that's our old Wi-Fi password, so the security guys won't complain. Don't get any ideas. So, if everything is working correctly, yeah, we have a working connection. Excellent. So, simple enough. Once you know where the steps are, it's kind of like Columbus's egg. Otherwise, you can fumble in the darkness trying to find these steps. Next thing, you don't want to be typing passwords all the time. So you put in access keys so that your user can talk to any other node without any authentication as long as it's over SSH. So usual steps, you generate SSH keys, you put them in the appropriate locations, and you set the right permissions for the right files, and then it all works. This is, we set the passwords previously, so if the keys don't work, or if you forget to put the key in place, there will be fallback to password. You don't get locked out. And in fact, usually the way I set it up is that I have keys from node 0, from the head node to the rest of the cluster. I don't have keys end to end. If node 2 wants to connect to the master or to the primary, whatever you want to call it, then you have to type the password because it's an unusual connection direction. But for primary to secondaries, it's all covered by keys. Now, one thing that the Pico cluster kit does very well is that it includes some scripts to do these things. genkeys.sh pretty much automates this process. And so you'll type in the passwords, and it will put everything in place. And once you get the presentation, there are links to the scripts from the Pico cluster crew. In this case, it's pretty much straight up this. Another thing that's worth mentioning is Dustin Kirkland's SSH Import ID, which is a tool that is downstream on Ubuntu. I think it should be upstream in Debian at this point, so it should be available for Raspbian. Use this to import the keys of a user just by saying, import the key of this user from Launchpad, import the keys of this user from GitHub. So it's a good way to give people access even when you don't know them yet, or you don't want to exchange 3 emails asking them for their public key. It just pulls them from their GitHub or Launchpad profile. Very convenient. So the other things that are already included with the Pico cluster automation are these things. Resize RPi is basically extending the size of the cards so that the images for the operating system covers the full size of the SD cards. And then you have a test facility, which works like so. And pings the 3 nodes and for all the nodes that you have, and gets back, in this case, the f-h. The other 2 commands are to reboot the entire cluster or critically to stop all the nodes. Since these are SD cards, it's not that hard to corrupt an SD card file system by just pulling the power. So stopping the nodes and having a clean shutdown is critical. While I was preparing the talk yesterday, I actually corrupted one of the cards just by tripping the power supply. I didn't forget to turn off the board. I just didn't have the option. I just tripped the wrong cable. So these scripts make it a lot easier to maintain proper hygiene. One more thing that I would do is that I prefer to have these things in a proper place, which is the bin directory of the user. And because Raspbian is a Debian derivative, you can just create the bin directory, and then at boot, Debian checks if the user has a bin directory and adds it to the path. So you don't need to add it yourself. It's self-adding. You can just move things in there once you have them squared away the way you like them. Also, I hate the .sh extensions for shell scripts, so I yanked those. But other than that, those scripts are pretty much good to go as they are. Maybe you need to change some usernames if you rename the usernames like I do. So that gives you cluster automation basics for things that you're going to do all the time, like stopping nodes or restarting nodes. But what about things that you're going to do only once in a while and that you need to do from all nodes? For that, there is parallel SSH. So in the example here, we're going to all servers specified in the nodes file and reading what's in the hosts. Basically checking that the static network configuration is done correctly. If you look at the second example, that is how you look for a problem. Or let me just show you. So, oops, I copied one character more than I meant. Oh, I didn't mention this, but for an intro level audience, it would be worth mentioning that in the slides, what I preface with the $sign means unprivileged user. What I preface with the £sign means root user. It's a shorthand to avoid writing, do this as root all the time. I should have just typed instead of trying cut and paste. What? Oh, and there is even some Unicode thrown in. Do you see the quotes there? So I guess we will just type. So this is the way parallel SSH usually works. It just tells you, I got a good exit code, isn't life grand? But it doesn't show you what actually happened. And this is the second example. If you go and say inline, you will actually get the output. So you can check what's happening on each node. And you will see, well, there is a Raspberry Pi, localhost, alias, I'm not sure why. And maybe you want to get rid of that. There is also a PC4. Well, this cluster really has only nodes PC0 to PC2. We could drop those. In any case, that's the core of parallel SSH. You could similarly check connectivity. Let me see. Where is my cursor? So what is H nodes? H is a way you specify where you want to go, H file. So the nodes file is just one host name per line. The other way you can specify this is that you can have capital H, and you can list the hosts individually. -C1 -W5. Yeah, let's say 5. Okay, this one again, I didn't use the inline, so I just get that everything succeeded blindly. The reason why I timed out the ping with ping only once with C and stop after 5 seconds is that if this failed, it will most certainly fail in honor of our keynote speaker this morning, and it would be a DNS resolution failure. So if you don't time bound it, it will try for 3 minutes, and you'll be waiting. On success, obviously, it returns immediately. There is one more thing that is an obvious example here. One thing that you'll be doing all the time is updating the nodes. So you can dispatch a sudo update to all nodes this way, and then you can actually upgrade all the nodes if you're that trusty. Time. Time is relatively simple. You just go to systemd, time date control, get the current status. You can get the results out of the other location, and you can get the actual definition of where the time server is in the systemd file. Now, to be able to do something useful with the cluster, you have to have a place where the files are. So just like we don't want to be changing permissions all the time, so we create one user across the entire cluster, we make authentication safe but transparent, and we give everybody the same user ID in case that ever matters. The other thing is that when you're writing code, you don't want to be copying new versions of the files around all the time. So you set up an FS. In this case, because of how flat the hierarchy of users is, it's really trivial. It's 3 lines to set up the NFS server and 2 lines to consume it. The only pitfall here is that the mount is coming from fstab in the client. You're going to be editing etc fstab, and if you get that wrong, the boot sequence of that node will fail. So do not fat finger edits to fstab. But other than that, this is pretty much all that you need to do, and it looks like this. So on node 0, we pretty much added this one line saying everybody that's on the subnet that these nodes have the private physical network on can access without password. Since that network is physically separate, why not? And SSH, let's try another node. And this line here is basically mounting the share on the first secondary node. Okay. Besides the fstab corruption, this is really the simplest NFS setup that I've ever done. So no complaints whatsoever. Now, what else? Last bit of configuration for the cluster is how do we use the lights that I was talking about. So we have arrays of LED lights on each board that can be used to relay status. There are 8 lights and they are RGB, so you could decide that each light has an independent meaning based on color. You can do something pretty obvious, I guess, like this. So let's start using our export, our shared directory that everybody has access to. So we have just one copy of the script for everything in the cluster. And basically, this is just scanning the LED. It's on the side of the box, so we'll turn it. And we can do pretty much the same thing. But I'm going to be lazy and not type it. And we can pretty much dispatch the same command to all boards. Now, this is funny, and it invites whatever silent jokes you want to put in here. But it's much more relevant to show some actual useful data. So let's try to do that, shall we? So first of all, let's clear those signs, and then let's try to, well, let's just do the top one instead of blinding everybody with too many LEDs. So this should be running only on the top one, and this is pretty much showing the load average of that node. So if I go over here and I need a second terminal. Where I put my second terminal? Here. PC0. $240. I'm just logging in a second time. So there is a command called stress that is used to put load on a system, and I'm going to launch two CPU stressors on this. On this node. And now you see that it's higher. And as soon as I kill stress, it goes back lower. So you have a little bit of visualization of what is going on in terms of the CPU load. You can write, these are pretty simple Python scripts. So you could write whatever Python visualization you want about the state of the individual nodes of the cluster. And that is one more thing. Let me see. What do I have here? Okay, clear? Good. These arrays can be programmed in Python 3, in Python 4. They're pretty easy to use, so not much surprise there. The only caveat is that you need to have a little bit of pause between the updates, otherwise you see as much flashing as you have seen right now. Maybe the speed of update is not as prized as not giving people seizures with too many flashes. So maybe slowing it down a bit would be a good idea. But that's entirely within your control because these are 20, 30-line Python scripts at best. Most of the work is just getting the data into a form where you can get to show it. So here. Let's see. So why is this a supercomputer? It is a supercomputer if we start using the message passing interface. So most parallelism in the supercomputing sense is done by passing different data to the same compute code. So multiple data, single code is basically the prevalent model, and that's what MPI does. You write a segment of code that's meant to process one problem, and then this the data region is being fragmented based on however many cores or however many CPUs on however many systems you have. From the point of view of MPI, it doesn't really matter if these cores are all in the same processor or if they are on different processors or they are on different systems. Obviously, the farther apart they are, the slowest the communication will be and the higher the overhead. But from the point of view of the code, it's exactly the same thing. Now, I documented what you need to install to make this work, but we're obviously not going to do that. The MPI compiler is MPI-CC. It is pretty well-established technology. You can find it on any Linux distribution you want to think of. And we have a couple of examples. So let's try this call prox example first. So this one doesn't do any computation. It just tries to split a workload into multiple chunks. And I think I'm sorry? Oh, sure. So we're going to go. This is one example. It's a very simple bit of code. This comes from a book by a NASA scientist called Carlos Morrison that was writing books about Raspberry Pi-based supercomputing already, I think in 2016 was the first time I saw something. This is his simplest example, and all that it's doing is splitting the problem into a sufficient number of data segments for the number of resources you asked for. So MPI exec is how you launch a C program compiled to the MPI interface. -N8 means that I want it split in eight ways for data, and then that the executable is called callprox, which is the code that I built using the example in the slides. the code itself is not doing anything. It's just allocating the different threads and then joining the results at the end. And so we can do this with 8. We can do it with pretty much any number that we please. It's just going to change the split of the data. Nothing too surprising there. The other part, the other example that we had here on the slides is this. At the bottom of the slide, you see that -H, where instead of saying, give me 8, I'm saying, I'm giving you these cores. Now, the way you address cores in the syntax is that you basically give host names. And in this case, I'm giving a host name of secondary node 2 and secondary node 1 4 times, because I know that these machines have 4 cores. So if I do things this way, what I'm going to get is, let's see, 607. Oh, where is my cursor gone? Here. Yeah. Same result, but if you compare to the previous one, previously all the 8 threads were on node 0. Now they're running on 2 different nodes. We're actually sending the data across the cluster itself. And we have 12 cores in the cluster, so we could go all the way to 12. We just haven't because it takes a lot of space on the screen, but we can do that. So here is a different example. We're running here this code that's called MPI08B. This is another code from Mr. Morrison's book. And all that it does is it integrates very slowly. It integrates the first, I can't remember how many digits of pi, I think 48 digits. There is a very long tradition and a very large number of codes to try to calculate pi faster and faster, and Morrison's book has at least 3 or 4 different codes to do this. This one is an interesting example because it allows us to do this in about a minute a run, so that you can actually see it. So I'm going to chunk this up in 100,000 integration segments. This is numerically approximating integral, and it's going to do it with 100,000 slices. With 12 cores, as I've given it right now, it should take about 25 seconds or thereabouts. While it's running, let me mention one more thing in the slides here. So the easy way to measure execution time is just to say time before the command itself, and that will run the bash built-in time, which most people should be already familiar with, but this is an intro-level session after all, and it will just tell you how long in wall clock time it took to run that command, and how much kernel time and user space time was consumed. Now, I want to run, I went and run those 2 examples earlier. The one with 8 cores took 26 seconds. The one with, actually no, the one with 4 cores took more than a minute and a few seconds. I can't remember if, yeah, the one with 8 cores, I don't remember how long it ran, but the one with 12, which we're running here, should have taken, this one didn't work. Oh, I know why. Yeah, it's my fault, as usual. We were idling in the time variable because I didn't give it the 100,000 input while I was talking. When it is not holding there waiting, it takes 25, 26 seconds. This is using 12 cores. And I was telling you before, when you are using only 4 cores, it takes about a minute. So we are making it 50%, we're making it twice as fast. We're making it so that it takes 50% of the time, but we're using 3 times the resources. So that's why there is that humorous quote there from modified version of Blade Runner, because there is overhead to parallelism, obviously. You are wasting a lot of resources. This is codified in a number of formal laws, like Amdahl's law and so on. But effectively, you are not going to get linear speed up. You're losing some performance. So if it took you X with 1 resource, when you go to 2 resources, you're not going to get 2X. You're going to get less than that. Now, if you could get linear speed up, it would be awesome, but you can't. It declines and declines, and it approximates a number that I'm not going to go into. But the important bit here is that you can throw resources at the problem, but only so far. And obviously, it's going to cost in time and in CPU. For many cases, it's a fine trade-off. It doesn't go indefinitely, however, which is why usually when people are reading stuff and you say, I'm going to make it twice as fast, they raise an eyebrow. When you say, I'm going to make it 10 times as fast, they go to Amdahl's law and various collated things, and they just go, that's impossible. You have to prove it to me that you can do it 10 times as fast, because up front they know how difficult it is. But 2x, despite the fact that marketing almost always lies, and it's not true that things are twice as fast, 2x is possible, and sometimes it's true. And certainly, in terms of parallel computing, it is possible to get 2, 3x reasonably easy. It's beyond that point that you really need to get to the details to see if you're getting a real fair comparison, or if people are changing the terms to show you good numbers. In terms of the hardware that we're looking at specifically, the biggest change going between the Pi 3 cluster and the Pi 4 cluster is not the fact that the Pi 4 cluster has twice as fast CPUs and that those are Pi 4s with 4 gigabytes of RAM, so we have a lot more RAM. That doesn't matter. What matters is that the Pi 3 has the fake gigabit Ethernet, and the Pi 4 has real gigabit Ethernet. So the performance improvement from Pi 4 is coming from the fact that you have real switching there. The overhead of distributed computing is almost always coming from the network. So first you have the problem of how many ways you're going to split the problem, and can you split it in a sufficient number of small pieces without getting buried in overheads. Then the second bit is going to be, is the network fast enough? Because the network is way, way, way slower than the CPU. And there are many humorous visualizations of that, basically saying something like, well, one thing is going over there, grabbing a sandwich and having lunch. Another one is driving to the farm, collecting the lettuce, killing the pig, making a prosciutto, and 3 months later coming back here and having a sandwich. That is the comparison in speed between what's going on in the network and what's going on inside the CPU. And that is not a joke. Those are the same orders of magnitude, 3 months versus 60 seconds. That is why the switch is so critical in this case. Of course, you can only go so far with Raspberry Pis, but you can build this, the most expensive thing that's on the table, you can build for $400. So this is a reasonable setup to train a student in terms of how to do MPI programs. It's a reasonable way to develop protocols for how are you going to manage upgrades and distribution of keys, or the stuff that I was describing at the beginning. Obviously, it's not the real environment to do your supercomputing. But you can write the program here, and once you have the program working, you carry it over to the expensive hardware. it should be compiled just fine and should just run just fine. So it's a convenient, cheap tabletop supercomputer in a sense. And obviously, when you have a real supercomputer, you have real switching. You can get 30 gigabit, 100 gigabit, whatever it is that the amount of budget allowed you to get. So I hope that I've given you at least one or two useful thoughts. I took some time to build out. This is kind of the first revision of this. I'd like to add a few more numerical codes and a few more examples going into detail. If there are ideas, I would be interested in hearing them. If there are questions, I would also be interested in hearing them. Remember that speakers are Pavlovian devices, so we need feedback to know which way to go. There is also going to be, at least I plan to have an article on this on opensource.com, so at some point you'll have all the notes properly written instead of shared as a bunch of slides, which are not exactly a good tutorial for documentation purposes. And that's what I have. Questions? Yes? Not really with the Pi, because the problem of the Pi is that everything is going through the USB controller. And so even Ethernet is going through USB. So it is rated at 1 gigabit. The interface, the SPI that's putting out is 1 gigabit, but the performance is not. There are probably other boards that are a little bit more performant than that, but as I said, the Pi 4 has real gigabit Ethernet, but it's 1 gigabit. I'm not sure if there is an SBC that's able to provide you 10 gigabit. I haven't seen one. So at that point, you have to move into the real hardware kind of game. Yes? Can you run a multi-node database on the Raspberry Pi? Like MySQL? Yeah, you definitely should be able to do it. I think that the binding limit there is memory. The Pi 4s with 4 gigabytes seem like a reasonable choice for that. Yes. Yes. SD cards. Yeah, I think it's a SPDX, but it's 32 gigabytes. I think the limit is the same. Yes. Yes. A mini cube? Oh, hosted here. Yes, actually, while I was musing about breaking one of the nodes yesterday, Rob Hirschfeld, who's one of the former board members of OpenStack, and he has his own company doing bare metal provisioning. They changed names. I think it's Digital Rebar is the current name. If you send me an email, I'll give you the links. But basically, he sent me a note saying that he had made automation so that you could go from bare metal to Kubernetes in a 3 or 4 node Pi cluster using his system. So that seemed like an interesting demo. I haven't tried it, but Rob usually does excellent work. Yes? Yes, but because the network performance is the bottleneck, caveat emptor. But it will work. It will work. It's just a question of how far you can push it, right? Yeah, you're not going to establish any speed record, but if you look at it, I have clusters in my office where I build these clusters that I like to call the slowest clusters for X. And basically, all that they can do is running X. You can never put any load on them, but you can actually see this code in operation, which is what I'm interested in. And so if I can do that with less than $10,000, for me is a win, because it would be the cost of one machine. Obviously, none of my clients would do that in production because they would laugh. It's like, how many transactions can you serve out of this? I don't want to serve any transactions. I just want to see the code running. There was somebody else, but I lost track of the hands. Yes. General parallel computing textbook recommendations. It's always been an area where there's been not much that's been good. And that's going back 30 years. For MPI, the best stuff is coming out of the MIT press. I think that they updated, at some point in this decade, there was an updated version of the MPI book out of the MIT press. That was the most recent version. There is a lot of excellent material for parallel computing done in GPUs, so NVIDIA and that kind of acceleration, or even Intel, what is it called, Knight's Corner, and those type of accelerators, which actually resemble clusters more than the NVIDIA environment does. For those, you can find reasonable documentation, but for supercomputers proper, it's really hard. Actually, we have the publisher of No Starch Press at the conference, Bill Pollack. You should pitch him a book on that. All right. Thank you.